forward to the front. You are screen sharing, okay?
Repeat problems.
All right. So I think the tech is up and running. Our next speaker is David Grynkiewicz.
Okay. I'm very happy to be back at CANT again. It's been a few years since I've managed to make it out here, particularly in person, and it's good to be back. Thank you all for coming. As the title indicates, this is the second part from the second talk, and so I'll go over some of the stuff we've already seen and some newer stuff too. So as Alfred said, it's going to be some more positive results, even though negative results are also good to have. So our setting here is zero-sum sequences, and we have our abelian group, and we have our subset G naught inside our abelian group. And what we're looking at are sequences of elements from this abelian group. And we're going to use multiplicative notation for our sequences. So we write a sequence as a string. So it just looks like this multiplicative string here, G1 up to GL. So the elements G1 up to GL are the terms in our sequence. Here's an example here, the sequence 1, 2, 1, 3, 3. So that means that the sequence has 1 repeated twice, 2 repeated once, and 3 repeated twice. So they're like multi-sets. But we're going to use all the language of sequences because that's the tradition in this area of combinatorics, and all the language from the free abelian monoids because that's the applications are in algebra, and it's good to have some flexible notation to deal with all this. Anyways, this is just a string of elements, a sequence. Think of it as a multi-set. You don't need to think much more about that. And since we have elements from an abelian group, we can add them up, and their sum is then just the sigma notation, sigma for sum. Add up G1 up to GL, that's the sum of terms. And so, of course, we're going to let f of G naught be all the sequences, finite unordered strings of elements. And B G naught is all the zero-sum sequences. So these are just the sequences. When we add them up, they add up to 0. So 1, -1, that's a zero-sum sequence because 1 plus -1 is 0. There are lots of other ones. Now, of course, as Alfred pointed out, if we have zero-sum sequences, we can multiply them together, right? You have a bunch of elements which add up to 0 and another elements that add up to 0. Then their concatenation is just like the union of the multisets. That just also adds up to 0 because it's 0 plus 0. There's also an identity element, right? If you just take the sequence with no terms, that doesn't change the sequence. So you're adding nothing to another sequence, it stays the same. And we have a nice cancellation property, which is easy to see. So we have a cancellative monoid. And there are lots of other cancellative monoids. And these are the ones that are more of interest from, say, algebra. So we have, orders and algebraic number fields, Dedekind domains, Kroll monoids, the examples that Alfred was talking about from last class. These are the algebraic motivations for much of what I'm talking about here. And it all gets reduced down to a combinatorial setting where we just use combinatorics afterwards. So if we have just a general monoid, right, we want to talk about factorizations. And so the easiest case of factorizations is when we start off maybe with, the integers, and you factorize things into primes, and you have unique factorization there, but you have more general settings where we know unique factorization doesn't hold. So we factorize things into irreducible components, which we're going to call for short atoms. We don't want to keep on saying irreducible element. That's too much of a mouthful. So we say an atom, that's just an irreducible element. It can't be broken down to anything further. This isn't in the case of the integers or the primes, because we have unique factorization, prime and atom coincide. And we want to look at the different ways to write our element, which will later be a zero-sum sequence, as a product of atoms. How can we do this? We're going to use A of H for the set of all atoms. And here is a typical factorization, say, of 12 inside this monoid of just the natural numbers. 12 is 3 times 2 times 2. And that's up to order of terms, the only way to factorize the element 12. But of course, it's going to fail in general because unique factorization is more of a rare property than a common property. And so we don't want to give up just because in most settings we don't have unique factorization. I mean, there are other ways to deal with this, maybe passing on to ideals, but you still sometimes want to care about the elements too. We'd like to say at least something about the factorizations themselves to understand, like, what is the difference between a setting where you have in some kind of monoid of maybe algebraic interest? When is the factorization completely wild? It can do whatever it wants. And when is there some kind of control over the factorization where there are restrictions on how the elements can factorize? And so that's basically the questions we're interested in. And we want to reduce this down basically to this combinatorial setting. And so even though the motivation is all coming from the algebra, these algebraic monoids of interest where we're studying factorization, we want to turn into something we can get our hands dirty with and use combinatorial methods to actually give some positive answers for. So one way we want to measurize whether or not factorization is completely wild or how nice it is something called the Kätner degree. And I know Alfred didn't talk about this. He mentioned some other definitions, but this isn't so hard to understand. So let's just say we have two factorizations of an element, and we'll call them Z and Z prime. So those are like formal products of atoms. You know, they say that the 12 was 3 times 3. Wait, no, 3 times 2 times 2. Let me try to get that right. There were a double. One of them was double. One of them wasn't. So, and that's just a formal product of atoms, a formal product of irreducible elements. And there might be other ones in a more general setting. And so we have two factorizations of the same element. We want to be able to transform one factorization to the other. So we start off with Z, and let's say we could take, you know, it's a bunch of products of atoms. We take a small subproduct of those atoms, you know, some of the primes, or in this case, the atoms in the factorization, and we take that subproduct, we refactorize it into another small number of atoms. So we're just sort of modifying the factorization by a small perturbation. And say we only use at most n atoms, a subproduct, and we refactorize into at most n atoms. We're going to say that the resulting difference between these two factorizations is bounded by n, because we've just taken n factors at most and refactorized them into n at most any other factors. And so we've, by a small perturbation, changed the factorization Z into Z prime. And so the idea is, here's the pictorial thing. Here's the factorization. Here are the m factors. Say we just did them first, and they've been transformed into n factors, and these are both small. So that's how we're modifying the factorizations, just a small number. And if the number of factors in our factorization is really large, we're not doing much at a given step. And the catenary degree is basically saying, well, can we take any two factorizations of the same number, of course, the same element? And if we start, however far apart we are, can we just slowly modify a small number of factors and change them up to a smaller number of factors? And just in a sequence of refactorizations, transform our factorization Z into Z prime. And if we let this C of H, the catenary degree, be the smallest number for which that is possible, or infinite if it's not, then that's going to be our measure of control. Because if this is a small number, if it's infinite, then that would sort of mean we can't really change one factorization to the other. But if at least it's finite, that means as the length of the factorizations grows, which tends to happen, we can always just, in a sequence of small perturbations, change any factorization into another one. And if it's even smaller, if we have bounds on how small it is, that tells us how much control we have over the perturbations, how small we have to, how lax we can be in how, to perturb one thing to the other. So if it's a large number, we need to allow a little bit more space for a global bound to transfer one factorization to the other. And as they get smaller, we just transform by smaller perturbations each time. So this is an example of an arithmetic invariant. It's going to be used to sort of decide whether or not factorization is wild or somewhat tame. Because if the catenary degree is finite, that means we can transform factorizations one to the other with small perturbations. And the smaller it is, the more restrictive we can do this. Yeah.
Yeah.
Okay.
Thank you.
All right. So now that we move back to the setting of the combinatorial setting, what does this mean for a monoid of zero-sum sequences? So we're starting off here with a zero-sum sequence. It's just a bunch of terms from our group, our subset of the group G naught, that adds up to 0. But of course, we might be able to factorize that into smaller subsequences that also add up to 0. So an atom is going to be basically a minimal zero-sum sequence. So it has to basically terms sum up to 0, but there's no proper subsequence which sums up to 0, because then its complement would also be a zero-sum sequence. And so when we're talking about a factorization, we're sort of taking a zero-sum sequence and partitioning the terms into minimal zero-sums, where those sequences can't be broken down into smaller zero-sum sequences any further. they're sort of almost like minimal linear relations. If you sort of think of them as you had sort of a linear relation of elements adding up to zero, some kind of dependence relation. If you have a minimal one, you can't sort of break that down into anything smaller in terms of these multiplicities. And there are different ways to decompose the zero sum into minimal zero sums, these atoms. And we want to figure out how we can factorize them. And the number of atoms inside the factorization is then the length. So our goal is to determine for an algebraic monoid whether or not we can control the factorization. And there are various ways of doing this. The Kätner degree I've just focused on at the beginning is the one I want to talk about for the most, but there are lots of other invariants that we could use to sort of measure control of factorization in a given setting. But for concreteness, I'm focusing on the Kätner degree right now. So we want to know how small this is and if it's finite. And as Alfred was talking about, we use these monoids of zero-sum sequences as sort of this universal object, where via these transfer homomorphisms, everything gets reduced down to the monoid of zero-sum sequences. So then we can just work in the combinatorial setting. So let's just briefly review. If we have our G naught being a finite set, as we mentioned in the last talk, then the Davenport constant is finite. And everything, and that means the monoid's finitely generated, and things get, all our arithmetic invariants can be sort of, for very basic reasons, finite. So here, for instance, you can use the Davenport constant to control the size of the Kätner degree, and it ends up being finite. And this is fairly straightforward. And in some sense, it's more of interest to measure the size of the variance here, because we know automatically for free and very easy arguments that everything will be finite in this case. Now it gets a little bit more complicated if the group is no longer finitely if the set is no longer finite. So if the set is no longer finite, that means our monoid is unlikely to be finitely generated. But we could still have the case that maybe the class group that's generated by G naught is finitely generated. And so that's one case over here. And if that's the case, then even though we don't have a finitely generated monoid, the class group is finitely generated. And this can be dealt with. There's interesting behavior here, right? So sometimes, yes.
The first line, G0 is infinite finite.
Sorry, just ignore that's a typo. The finite should not be there. Just ignore the second finite there. I'm not sure what happened there. Sorry. We're just looking at when G naught is infinite, but the group it generates is finitely generated. It's not infinite finite. I'm not sure what happened there. Right. So in this setting over here, we can have, it's no longer guaranteed that the invariants are finite. Sometimes they're finite, sometimes they're not. And with a lot of effort and some more advanced tools, you can sort of study this and know what's going on. And so basically the case of finite G naught, well studied, everything is trivially finite or finite for very basic reasons. Upper bounds, getting more precise upper bounds, difficult, but that's a lot of the work is in that direction. If the class group ends up to being finitely generated, interesting dichotomies occur. Sometimes you have well-behaved factorization, sometimes you don't. It can be a lot of work to distinguish the two cases, but with tools from convex geometry, you can say at least some things. But for infinitely generated groups, basically no one had even considered this question, because it was basically, you just was kind of assumed that in the infinite generation case, all bets would be off. It would just be wild. I was just assuming that myself too. And then when this project basically started a few months ago, Alfred just kind of was like, let's look at, infinite torsion groups. And a little bit surprisingly, there can actually be control factorizations in these settings. And so that's what I want to be talking about. Alfred talked about some settings here where a certain parameter, this K-inf, was 0. And then, as sort of expected beforehand, everything became wild. Even this very basic union structure theorem for unions doesn't hold there, which we might have expected in general. Obviously, our expectations were wrong, because we're going to see that we do have control of factorization here. Right. So this is these cross numbers that Alfred defined. It's the cross number of an element is just the reciprocal of the order. The cross number of a sequence is just the sum of all the cross numbers of its terms. This is basically a different way to measure the length of a sequence. The length of the sequence is the number of terms. Here we're weighting. This is like a weighted length, where we weight each element with the reciprocal of its order. And this makes sense, because then we can talk about things, even though the Davenport constant is infinite, you could have zero sum, minimal zero sums of arbitrary long length. You might not have arbitrary large cross number for those sequences. So we have at least some measure of size that is still sort of globally bounded. And that's why this is going to help us out. Now, these are the three constants that Alfred talked about. So this little k, the little cross number, it's the sort of the maximal cross number of a zero sum free sequence. That basically means if your sequence has size, its cross number is more than that, it's guaranteed to have a zero sum subsequence. The sup is for those that are more familiar with this, we just drop the sup. This is just the maximum size of the cross number of a minimal zero sum sequence. And the new constant here, which we had to introduce to study this more general setting, is the inf. It's the smallest size of a cross number of a zero sum sequence. So you look at all the zero sum sequences, and there's some global bound that separates it away from zero, assuming this is non-zero. And basically, in the previous talk, we have a setting here where the two invariants, the more classically studied ones, were finite, but this new one was zero, and basically wildness happened. Even that structure theorem for unions failed to happen. You don't have nice structure in the union sets there. So and all the other invariants, such as the catenary degree, which I'm talking about, were also infinite. Nothing is well controlled. And in contrast, this is one of the results we have in the same joint paper, that we actually have an upper bound for the catenary degree in a fairly general setting here. So we just have a non-empty subset of an abelian torsion group. This could be any abelian torsion group. So you're probably going to think this includes non-finitely generated groups. Here's the catenary degree, and we have a max of two things here involving these three cross numbers over here. So as a particular consequence, if those three numbers are all finite, if the small cross number, the big cross number, and this inf is positive, that means the catenary degree is finite, and that we have control of factorization. It gives us actually a concrete upper bound for it. And another nice thing about this is this bound is actually tight. We were actually kind of surprised. You could probably prove a bound of some sort, of that sort there, that says if those three cross numbers are finite, then you could do a fairly simple argument and show that that would imply the catenary degree is finite. That can be done without too much effort. So one of the nice things about the bound there is that with a bit more effort, they're getting that optimal constant too. You can't actually beat it because there are some simple examples that show that this is the best thing possible. So for instance, here, this is just well known. I'm not going to go through the details, but these are the actual values in this particular case here. When you take, the group Z2, a finite field over the P equals 2, dimension R, these all numbers are all easy to show. And if you check in here, both these bounds equal R plus 1 in that case. Second example, if we take a cyclic group of prime power order, again, this is maybe a little bit more advanced, but this is all classically known. The values of all these constants here can be computed. And again, in both cases, they equal the Q on both sides. So we have two infinite families of groups where the bound can't be beaten. That means since we have infinite families of groups, that constant 2 is basically asymptotically best possible. We couldn't improve upon this bound anymore. Now, obviously, if we restrict to more restricted groups, maybe if we say our example is not of this form, maybe there can be better constants there. But if we have just a general bound, something that has to hold for all possible monoids, all possible subgroups, this is going to be the best constant we can have. So this was a nice positive result. And I'll talk briefly, so much time left, just a sketch of the proof of some of the ideas that go into here so you can get some idea of what's going on, right? So we have our factorization, right? There's one factorization, decomposition of S into atoms, minimal zero sums. Another one over here, V, we want to transform one into the other with small perturbations, right? So that's our goal. So we're going to take, our arbitrary atom U1, and it's going to divide some subproduct of the VIs because these are subsequences. So that just means this U1 is contained in this multiset there. And let's rearrange the terms. And so it occurs in the elements V1 up to VS minimally. And so that's what we need to get this to happen. Right. So the basic idea is that if we remove U1 from this sequence here, we have some leftover terms. And if the number of those leftover terms is bigger than that little cross number, the definition of the little cross number would guarantee there would be another zero sum that was disjoint from U1, sort of contained inside this product of the V1s. And we would be able to refactorize that, say we call it the V prime and pull it out. Because this is disjoint from the U1, U1 will still divide just this new subproduct instead of the old one over there. And now it will divide a smaller sequence in the sense that the cross number that it divides gets smaller. And then if we can get some control, anyways, over the size of how many T's and T primes we need to refactor each time, we'll just iterate this process. And if we iterate this process, then the sequence right here that this V1 up to VT where it's the dividing is going to get smaller because each time we're pulling out some V prime, we no longer need the V prime, we throw it away, right? U1 divided V1 up to Vs. Now we can refactorize this with a small perturbation, remove the V prime and repeat the process. And the size of the sequence in terms of the cross number diminishes, and it can't go on forever because each time it's reducing down by this minimal cross number K-inf. And so eventually it stops and K1 ends up, U1 ends up being dividing the new factorization after this sequence of small perturbations. Then we repeat for U2 and U3 until we get retransform the one factorization fully into the other. And that's the basic idea of what's going on here. The main difficulties, which I don't want to go into, is basically optimizing this argument. So it's trying to find clever ways to make sure those S and T's are small. And that would just, I think, overwhelm me if I went to the details there. It isn't something that's quite as straightforward, but it can be done if you work at it a bunch and we get those optimal bounds there. So there's a little bit of time left. We have some other positive results too. So the catenary degree is not the only way to measure a structure factorization, right? This is this UK set, which is this unions of all length sets that Alfred was talking about before. And here's that same definition. Basically, we want to refactorize. You have K atoms, you multiply them together, you can refactorize them into other products. And they have different lengths, these products. And so we let UK be all the possible refactorization lengths of a product of some K atoms. And since we're unioning over lots of atoms, this is normally a very structured set, or this, it should hopefully be one. And the structure that we expect that happens in lots of situations for lots of monoids is that it's mostly an arithmetic progression, except for some globally bounded region near the start and the end of the union, where we're allowed to remove some terms. And if that's the case, then we say the structure theorem for unions holds for these union sets, right? The other important thing that Alfred mentioned is that half factorial. That's when we don't have unique factorization, but the number of terms in a factorization is uniquely defined. It's always the same number. There's that quasi-cyclic group. This is sort of, for instance, maybe the simplest case of a non-finitely generated abelian group, right? There are lots of direct products of this, but it's basically, we're just looking at elements mod 1. So we're in the integers, we mod it by z. 1 is 2 is 0. Any integer is just considered 0. And our denominators are restricted to powers of the same prime. So this is the simplest example, the basic building block for say, non-finitely generated abelian groups. And in this setting over here, we can also get some positive results over here. So even stronger ones that we get for our general torsion group. So the idea is here, if we have, say, our G naught inside this quasi-cyclic group, and we assume that the KM, let's just call it little delta, is strictly positive, so that our previous result would tell us that the catenary degree was finite, then, well, it's not so hard to calculate that the elasticity is exactly equal to this delta inverse, right? The catenary degree is finite. That's just the bound from the previous slide. What we also get here is that the H satisfies the structure theorem for unions. So it has this nice property that didn't hold for when the inf was 0. That was the example that Alfred was talking about from last class. If this K inf was equal to 0, there were lots of examples. We were able to construct examples showing that this structure theorem does not hold for them. We assume it's not positive, it's guaranteed to hold. And we have one second condition over here, which you should think of this as being sort of a partial structural characterization. It's not a full structural characterization, but it tells us a lot about the structure of the sequences. It's basically saying the only way we can have K inf being positive is if, there's some homomorphic image. We multiply all the elements of G naught by some power of P, and it maps it into a finite union of half factorial sets. And then the reason partly why this is a structure is that we know what the half factorial subsets look like inside a quasi-cyclic group. In a general group, half factorial subsets can be difficult to characterize. Or for quasi-cyclic groups, they look like this. right? It's just basically you fix the numerator and you just let the denominators go from, p to p squared, p cubed. And of course, the numerator, however, is going to be a p-adic integer. So we allow, it's this just infinite sum over here, but eventually it's going to divide out and be 1. And once it's an integer, it gets absorbed into Z. So it's all fine mod 1. These are what the half factorial subsets look like inside a quasi-cyclic group. And so when we're saying that this G naught is a finite union of quasi-cyclic groups of the half factorial sets, we know exactly what it looks like. We're taking some homomorphic image and it's contained inside a finite union of sets like this. And in fact, it's using the structure that allows us basically to get these extra stronger results in this particular case. Since it looks like I'm running a little close on time, I'm not going to talk about the proof ideas for this instead. We'll just maybe found this a good place to stop the talk right now, and we'll skip right ahead to thanking you all.
Questions for David? Which particular reason why the group has to be
Oh, just because the non-abelian case. Oh, he asked why abelian groups. So things get much more complicated for non-abelian groups. For instance, there's thought to be different notions of the Davenport constant. So the notion of an atom was just it had to be a zero-sum sequence that was minimally so it has no proper subsequence that's zero-sum. But if you're in a non-abelian setting, that's no longer what an atom means, because you can have a subsequence that has a proper subsequence, which is product 1, but its complement won't have product 1, because you can you have non-abelianness, so you can reorder the terms. You have to, of course, define what it means to be product 1, but
the sequence is formal, just formal, literally
a string of elements, yeah. But the order of terms is irrelevant for our sequences. They're unordered sequences. But the order of multiplying the terms together to represent the 0 element or the 1 element does matter. And so if you want to talk about a product 1 sequence, since the order of terms doesn't matter, you have lots of ways to order the terms. You have lots of different products for the same sequence if you're in a non-abelian group. So you could say that the sequence is product 1 if there just exists some ordering of the terms that has the product being 1. But the problem with this is that you no longer have this transitivity property. So if you have a sequence, you can order the terms so they multiply out to 1, and you have a subsequence, you can order the terms so they multiply out to 1. There's no guarantee that the complement is going to have some order of terms that multiplies out to 1, and that adds some complications. So people have studied these types of questions in the non-abelian setting, but they get a little messier. And seeing as no one had even tackled anything for non-finitely generated groups at all, we started with the simpler case of just the abelian case.
Thank David again. So we have a break for lunch for an hour. The dining room in this building is closed for the summer.
You want to hit yes?
Yes, I do.